Hi again, everyone. Welcome back. I okay, yes. So I can see I've had a question. Sorry that I've missed from someone in the meantime about the recursive function here. I suspect looking at that. Well, we'll see what happens. I might be able to help. So I said when we came back, we'd take a look at this recursive function to calculate the Fibonacci sequence. Let me start sharing my screen once again, and we'll take a look at how to do that quickly. Here we go. Okay, so I'll wait until that's popped up on the screen. I think it's hiding from everyone at the moment. So this is what I put on before, just as we were going to lunch. Some hints about what you might want to put in here. So let's try and work out what we want to do. First things we need to do, with this as our function prototype, I guess, we need to declare what n and nf are. So let's do that. Let's put in, first of all, that n is going to be an integer, and we want it to be in. It's not going to be changing in any way. It's just a number that tells us how to do something within the sequence itself. So that's going to be n. Then we've got the result nf, and nf is just going to be an integer. Remember, because it's the result, we don't need to give it an intent. Intents only go on the dummies here. So our nf is our return integer, like so. Everything else that we do now in the execution portion of the function is entirely in service of working out what nf is. So we need to do a little bit of logic depending on what that dummy value n is. I think I've actually got this slightly back to front, perhaps. I'm actually going to delete this, and I'm going to start here, and I'm going to begin with the condition that n is equal to 0. So if we're asked to calculate the 0th part of the Fibonacci sequence, then we set n equal to 0. nf rather equal to 0, sorry. We then need to consider another case. We'll make an else if here, and we'll say that this is then if n is going to be less than or equal to 2. And in this case, we can have nf return the value 1. And that's actually everything that we need now. So if we call it with a value n, which is greater than 2, then it's first of all going to come down here. It's going to skip past those first two, the if and the else if, and it's going to filter into the else here. And it's going to call then Fibonacci, it's going to call itself with n minus 1, which would be 1, and n minus 2, which is 0. So that's actually, I think this actually needs to be a less than or equal to 0, just to make sure that works. I think that's correct. Hopefully I'm correct. Yes. Would it be? Actually, it might be okay. I'll just leave that in case. In case we do somehow end up with a negative n, that would then return 0, which could be safer. I think that's okay. So we would call these in that way. Fibonacci, but if we call a number that's greater than that, it'll call Fibonacci however many times it needs to get down there. There are actually more efficient ways of doing this, but this way will work given what we started with in the material. Let's just try putting a call in there. So let's just do print star. What was the name of the? It's just called Fibonacci. Fibonacci. Let's just do print star. You're missing a then in my ifs, am I? That's very bad of me. Yes, just here. That needs a then. Else doesn't need a then, but else if does need one. Thank you for pointing that out. Okay, great. So let's just quickly try and do that. Fibonacci, I don't know, what should we do for 10? Should work okay. Remember that's in tens here, so that should compile without any issues and hopefully run and give us a result. Is that correct? I hope so. Let's quickly find out. Where's my Fibonacci 10? 55. Perfect. Okay, great. So that hopefully that answers any questions you might have had about doing that. Does anyone have any questions about that before I move on to the next section at all? Please just type in the chat or shout out if you do. Sure, yes, let me scroll over to it. Vim, the module, there we go. You can take a quick look again. Yeah, of course, let me just do that. You can see how it compares to what you've done. Of course, there is the solution. Remember, there is the solution available in the material as well. When I called it, okay, let me quickly do that. Remember, you can check this and just, I'll bring it up, I'll bring up the program. I just did this. So it's a function, so we can just use it in an expression like this. We could have also, if we wanted, we could have created an integer. Let's just say a, maybe II, I'll call it. I like using II. Is also perfectly fine. Okay, I hope that answers questions for people. You should be able to, the solution, so the solution module should have something similar. You're very welcome. Yes, so you can always come here and check. And I think that the program does something similar again to call it. Okay, so they actually call it in a little loop to show it's moving through the sequence. So you can do something a bit more fancy like that. But yeah, please remember you can always come here and check, the sample solutions. Okay, so with that, I think we'll move on. And our next section is on array dummy arguments. This is a fairly important section. As soon as the server decides it's going to send it our way. So we've covered a lot now about how to write functions and subroutines, how to pass those variables in and out, the dummy variables. But something that we need to take a little bit of care with, or give a little bit of thought to, is how do we do that with, here we go, how do we do that when our dummy arguments are arrays? Remember, we've now got to think about things like bounds and dimensionality and shape. And that means that we just need to spend a little bit of time understanding what's going on there. So there are really two ways, I guess, of doing this in modern Fortran. There are other slightly older ways as well, but we will not bother talking about those because they are not good at all. One is to do everything fairly explicitly. So you can imagine that you have a subroutine that's going to be doing something with an array called A. But what we might also do is pass in another dummy variable called nmax and give that intent in, and that's just the size of the array. A here is one-dimensional, it's rank 1. So here we're just saying that real dimension 1 to nmax. So we're saying the lower bound of A is to be 1, and the upper bound is to be nmax. And we're giving that intent in out. So here we're being completely explicit about what the shape and size of A is through passing in this nmax. If we wanted A to be a rank 2 square shape array, for example, we would just put comma 1 colon nmax in here. So we just have the same thing twice. If A were going to be a different shape, if it had a different size in the rank 2 dimension, in its second dimension, we would pass in, let's call it nmax2 or perhaps mmax or something, the other size in the other dimension. So you pass in its extents in each of the dimensions as dummy arguments and use those to explicitly say what the shape of your array is. So here we're being explicit again about what the lower bound is. You could just put in nmax and it would then assume that the default lower bound is 1. And again, if you want to change it to something else, you can override it. You could have it start at 0 and go to nmax -1 if you declared that here. You can do whatever is correct for your code. The other, and this is a way that's only possible in modern Fortran, is to do what's called an assumed shape array. And in this case, what we do is we don't pass in explicitly what those extents are. Instead, we do something that looks kind of similar to when we declared allocatable arrays, where we used colons as dummy extents, I suppose you might call them. And here these are both rank 2. But we haven't given them the allocatable attribute, because what we're doing here is we're saying that when the subroutine array action2 receives these two arrays, A and B, one is intent in, one is intent out, we're saying they're both going to be rank 2, so they're going to have 2 dimensions, and we're furthermore saying by leaving these blank, by just putting the colons in and nothing else, we're saying whatever size you get, whatever extent you get in each of those 2 dimensions, just take it. So we aren't saying you're going to be going from 1 to 10 or -10 to +20. You're just going to take whatever you get, and that'll be it. You do need to take a little bit of care here, because what's passed through is the shape, not the bounds. What that means is that once we're here now working inside this subroutine with A and B, we've now got 2 valid arrays, A and B, both rank 2, which we can work with, and they have shapes that are 2-dimensional. And in both dimensions, as we've declared it here, the indices will start at 1 in each of the 2 dimensions for both of them, and they will go up to whatever. That could be something completely different in the actual argument, and we will see an example in a minute. The code which calls array action2 could be passing in for the actual argument for A an array which starts at 0, and same for B. But when we jump into the subroutine here, because we haven't said anything here about what the first index should be in any of the dimensions, Fortran will again go with the default and say that they're both starting at 1. So although the shapes are the same, A and B will have the same shape as whatever they are in the calling code. The actual bounds on them in each dimension can be different, and that can sometimes cause issues. We will see an example in practice in just a minute or two. It's just a little reminder about array terminology. So something that can help, part of the way at least, is to use L bounds and U bounds. We did see these earlier on. So if you call these on an array, then by default it will return a rank 1 array, which gives you the bounds in each dimension. Oh, excuse me. But you can provide an optional argument as well, dim. So you say dim equals, and then you give it an integer of whichever dimension you care about. And in that case, it will simply pass back the integer, which in this case is the lower bound in the first dimension or the second dimension. The same if you called U bound. So it works the exact same way for both of them. So that can help. That can help you find in particular what the upper bound is if you're going with the default lower bound of 1 on everything. But it can still cause some issues. Let's check program1.f90 and module1.f90, see what happens, and try to understand just a little bit of what's going on here. So let's go to the terminal and have a look at what's happening here. So we've got module 1 and program 1. So let's just first of all take a quick look. Program1.f90, what's it doing? It's saying we're creating 2 arrays, A and B, and they're both rank 2, but they're indexed differently. So A is starting at 0 and going to the maximum size, Imax and Jmax, plus 1 in each of its 2 dimensions. So these are just 2 parameters that we've defined to say how big the arrays should be. So 0 to Imax plus 1, 0 to Jmax plus 1. Then we've got the second array, B, and we're saying that this one is going from 1 to Imax, 1 to Jmax. So you can, if you like, you can imagine that B is just a simple array, 1 to Imax, 1 to Jmax, but then you can sort of imagine, if you like, overlaying A on top of it, and A has the same shape as B, but plus 2 in each dimension. It sort of has an extra halo around it, if you like. You can actually draw a picture of this, which does help. You can imagine B as having a halo around it, and A contains that halo as well. Then what's happening here? We're filling A, the interior portion, 1 to Imax, 1 to Jmax, equal to 1. So the interior part only, not that outer edge around the array. And then we're completely filling B with 1. And then we're calling ARCHER2 twice. And that's the subroutine, which is coming from module 1. We call it first time with A and B, the second time with A, specifically 1 to Imax, 1 to Jmax, B. And then we print the values B. I'm actually going to, let me do this actually first. Let's take a quick look at the module 2, so we can see what's happening. The module is just adding them together. It's saying we're getting A, which is intent in, rank 2, assumed shape. B, intent in out, also rank 2. And then it's saying B is equal to itself plus A. So it's just adding the 2 arrays on top of each other. So you can probably see that something's not right already, because A and B are not actually the same sizes as one another. If I try to run this, it's just FTN, module 1 and program 1, it compiles and it runs, and we get some interesting numbers coming out. What were we expecting? I'll just show this. I think I think pretend this line doesn't exist for now. I think this is maybe confusing things a little bit. Let's just pretend that we're only doing these 3 lines. We're setting all of A's interior equal to 1, and then we're setting all of B equals to 1, and then we're adding them together. So this actually kind of looks a little bit like maybe a 2-dimensional CFD code or the like, or perhaps we're going to be solving a partial differential equation across a grid. In that case, you might have halos. Perhaps we're doing something in parallel. Perhaps the outer edge contains boundary conditions which are going to stay constant. That's what that kind of looks like to me here. That we're supposed to be doing something around the edges of A, the inside of A matters, and we want to be adding the interior part of A on top of B. But when we just do this, call AB, it's perfectly fine. The subroutine that we're calling doesn't see any issue with that because we've just told it. Let me save that. We've just told it to take whatever we give it and add it together. And it's perfectly happy doing that because it's lacking a few bits of information that are in the program which is calling this. And so again, if you kind of imagine the 2 arrays being overlaid on top of each other, what we're now getting is that A is shifted because remember, we haven't told it where the indexing should start. So Fortran is going to say, okay, everything here, the indexing starts at 1, except that in the calling code, we know that A is actually starting at 0. So we're getting an offset on that array. What we should have been doing is this second call, where we're correctly saying to use the internal part of A. And if we do this, if I compile that now and then run it, that's now correctly adding them together. We aren't getting the external part. When we called it the first time, the subroutine was working with a big chunk of A that was actually equal to 0 because we had never bothered to initialize it. We only ever did things with the interior part of A. Those edges of the array were just whatever, in this case 0, so we only ever added 1 onto them. Okay, does that hopefully make sense to people? This can be a little bit confusing. Does what we've seen here make sense? So a question, with the first incorrect call, why didn't we get an error when it tried to add A and B, which were of different sizes? It's kind of because the compiler is trying to be helpful, is I think the best way I can put it. As I say, when we come through here into the subroutine, we are losing a little bit of information. We're just saying it's rank 2, but who knows how big, essentially. So when it sees that we're adding them together, it's going, oh, okay, so they must conform, which isn't actually really the correct thing to do, but it is the best thing it can do in these circumstances. It's not a great situation, but we've kind of set this up to fail. The better thing to do would have perhaps been in here. Maybe can we quickly do it? Let's print star L bound A and U bound A. Let's see what this shows us. This might feel a little more U bound, sorry, L bound B, U bound B. Let's try this. So if we compile that, so that's us doing things correctly. We get that they're the same sizes. So the lower bounds are 1, 1, upper bounds 3, 2. So this is essentially showing us the shape. If we do it incorrectly, let's change this around again and save and recompile and run. you can see here that it is correctly getting that the sizes are wrong. But it's sort of, because it's going with assumed shape, it's sort of loosening the restrictions a little bit. It's sort of deciding, in this case, it's going to relax a little, and it's just going to go with what it tells us to do. It's not exactly, as I say, it's not a good thing, but it's the best it can do. So it does realize that these are offset, but it doesn't quite, because we haven't given it any information really on how to use these differently sized arrays other than that we should add them. It just goes ahead and does it because it doesn't have all the information that the program itself has. The program here has everything. The module has less to work with. Oops, I can't open the module. I mean, something else which we could have done would have been actually to specify this. So we could do this as well. We can specify here just the same what those indices ought to be, and this starts at 1. And in this case, I'm not actually sure what will this do. Will this actually work? This might work. I'm not certain. No, it's still, yeah, it's still just fitting them on top of each other. It's just relaxing things a little too much, and it's not really working. So this is kind of why, way to the material, this is why we kind of say you need to show care. You need to be very, very careful when you use assumed shape arrays in your subroutines and functions, that your indices are correct, both where you write your procedures and also when you're calling them. What you can do, what is in general a good idea, what I would do very, very definitely if I were writing this code myself for something proper, something in production, I would start putting ifs in here and do things like if L bound A dim equals 1 is not equal to L bound B dim equals 1. Oops. Then, I'd print a warning and, oh well, an error actually, and start doing stop and the like. That's what I would do. I would put lots and lots of checks in here, and it's a little bit annoying actually having to do this. It's nice that you have the option to do it, but it means you've got to write a little bit of boilerplate type code every time to do these checks to make sure that that the ranks of things that you're getting are correct. And also for the U bounds, you want to make sure that the U bounds, perhaps even more so, are correct, or just that these shapes are correct as well. So that's why I personally actually tend to prefer being fully explicit about things. I tend to do this myself just because I feel a little bit safer. It means that you have to bloat your list of dummy arguments a little bit. You have to put in a little bit more effort to say what the sizes and extents of your arrays are. But I think it's a lot harder to go wrong if you do this. Okay, I hope that answers the question. Does everyone understand this then at the point we're at now? Okay, I think so. No questions? All good? Okay, great. Thank you. Okay, great. Let's carry on. Again, if you do think about it later on and all of a sudden it stops making sense, just let me know and we can come back to it. So in just the same way as we can have temporary variables inside our procedures, we can also create arrays. So that's what we've got here: integer dimension size array, temp. So what we've done here is we've actually got two assumed shape arrays, A and B, and then we're just saying let's just create a new array called temp. It's the exact same size as A, and we're just going to use that to swap the contents of A and B. And yeah, you could have done it with a loop and a scalar as well. And these generally are created on the stack, so that's at least a little bit helpful. Although if they're huge, you can run into different issues, I suppose. I mentioned before lunch dummy arguments, which are allocatable arrays in the context of modules. I said that this is part of why using modules is very helpful. But you can it's perfectly allowed to have an allocatable array as a dummy argument. So here that's the array A, and what this does is it just allocates it. So this is intent out for the array, and intent in for the lower and upper bounds, and it just allocates that and returns it. There are a few things to remember, which is that the actual arguments that you give when you call your subroutine, in this case, when you call your procedure, must also be allocatable and have the same type and rank. So you can't use this to try allocating arrays which aren't allocatable. That will go very wrong. The array will be the wrong type of memory and in the wrong place and treated in the wrong way. If it's intent in, you can't start de-allocating it. So again, that's a form of rights protection on it. And if it's got intent out, but the array is allocated on entry, it will be de-allocated on entry. So so part of making things intent out, as well as just meaning that we don't care what it is beforehand, in this case, it's actually also kind of enforcing that the array will be wiped clean before you start. So I think the last one in particular is perhaps the most likely to catch people up. It's something that's comparatively easy to forget about. It makes sense if you think about it, but sometimes you just need to realize first, yes, the reason that my array is not allocated is because I made it intent out. So that meant that it was automatically de-allocated at the point that my procedure began. Yeah, and you can also, so you can go all the way here. Your function can return an allocatable array as its result. And if you do that, you can kind of think of it as sending a temporary array back, and that's going to be deallocated at the point when the calling expression has finished. So you're perfectly allowed to allocate the size of the array that you're returning at the point that you send it back. But of course, it's just going to be used in an expression evaluating it. Once that's finished, it'll be lost again. We have seen now some optional arguments. We saw that with our L bounds here. So dim is an optional argument, and this exists on a few intrinsic functions dealing with arrays, where you want to be able to tell it to specify particular dimensions. I think we saw it earlier with count as well, was it? And another intrinsic, I can't quite remember. But if you want to tell intrinsic functions to only work on particular dimensions of an array rather than all of them, that's a very common one to see. But you can write your own optional arguments when you do this. So for example, subroutine do something takes in an intent in A, and then two optional, one is intent in, one is intent out, flag and I error. So people might provide these as options, or they might only provide A, or they might provide flag or I error in any combination. It's a little bit clunky, I think, compared to some languages, and a little bit about how you set the default values, because you can't set the defaults here in the prototype line the way that you can, say, in Python. I think Python does it a little bit more elegantly. But Fortran, of course, has to let you set defaults somehow. So one way you might do it is like this. All of them all of them involve using the present intrinsic function. Present just says, was that optional argument provided? I'll talk about that in just a second. The questions that just came through. So you would set the local flag. So this is just one example of how to do this. You would set the value to actually be used within the procedure is equal to some default value, and then you could say that actually, if the optional argument was actually given, in that case, overwrite the local value with the one that was given as the argument. Okay, then we have a question in the chat. If you want to set I-error but not flag, what do you put between A and I-error? So in this case, what you would do is you would provide I-error equals. We do give a couple of examples down below. So this is what you're talking about here in this question, I think. If you have some combination of non-optional dummy arguments and some number of optional arguments, you will want to be in the situation where you want to call some of them and not others. We want to provide some of them. So you always provide the non-optional ones as positional arguments. You always put them at the beginning. So you just start off going A, B, C, D, the ones which do not have the optional attributes. And once those are finished, you can then put in the optional ones in whichever order you like, if you give it the keyword along with it. So there are some rules attached to how you do this, and I think this basically answers your question, Victoria. Yeah, it's just a matter of making sure that the compiler is correctly able to interpret those. Once you start putting in keyword arguments, you can't put any positional ones in anymore, because it stops making sense. You've messed up the order, if you like, and any further positions become meaningless. And positional arguments have to appear once. Keyword arguments you can provide not at all or once. I think that makes sense. It's just a matter of logic, I guess. Okay, so there's a challenge here now, and I think it's actually worth us doing this. I think this is actually quite a nice little test for us. So there was one of the two big exercises that we would have gone on to yesterday if we'd had time, was to solve a tri-diagonal matrix. So this is a bit of linear algebra. If you're used to this, this is solving. Maybe I can quickly draw this on the whiteboard. This is solving a matrix problem where we've got. Let me see. This is going to be horrible. Where we've got the problems A, X equals B. So it's always the case. We've got a matrix multiplied by a vector equals a vector. Some of you will be very, very familiar with this. Some of you may not have done this before. So we've got A, and then we've got X. Apologies for my bad writing, equals B. We know the matrix A. We know the vector B on the right-hand side. What we're trying to solve for is this vector of unknowns, X. Remember that a matrix times a vector equals a vector. So that you can imagine that there's this problem like so, where we've got some matrix, some right-hand side, B, and we want to solve X. This is very common for solving partial differential equations. There are loads and loads of applications for this. Now I've got to work out how to delete this. Eraser, there we go. Let's try and get rid of this. Can I just clean it somehow? Clean it all, clear annotations, yes. Okay, so this problem is trying to solve a matrix that looks like this in particular. So a tri-diagonal matrix has 3 rows of numbers only going down here. And my drawing with the mouse is terrible. I do apologize. So it's got a diagonal, which we'll call B, which you can represent just as a 1D, so a rank 1 vector, and then an upper diagonal, which we'll call C, and a lower one called A. And these have different sizes. So B is, so if the matrix is of size n, then B is of size n, and C will be n minus 1, and A will be n minus 1. I hope I'm remembering this correctly, doing it correctly. So that's our matrix A. So it turns out that there's a nice way to solve this with a little bit of maths. You can solve this because then we're just multiplying it by our unknown vector x again. And that's still going to be equal to B. So this is just a bit of background. If you actually don't care about this, you don't need to worry about this too much. We're just using this as a framework for some code which we'll be writing. So our goal is to write a bit of code. Well, it's actually written for us. Our goal is to take some code that solves X in this situation. I think actually it possibly calls, yes, forget. In this, we're actually calling the right-hand side D. So we've got 3 vectors for the matrix A, B, and C. Another vector D. When I say vector, think array, which is the right-hand side. And we know all of these. These are numbers which we know. What we want to solve is X. Okay, so if I share my screen again, we can actually think about doing this. So I think it's worthwhile spending maybe a decent bit of time on this actually. So we've got so you may have attempted this by yourselves if you went back to that section last night, perhaps, or this morning. Well done if you did. If not, don't worry. We can use this template here, exercise.f90. So this contains some code that uses Thomas's algorithm to do this problem, which I just drew on the whiteboard. So we've got the 3 arrays A, B, and C, which contain the contents of the matrix. And you can see in the declarations that they've been given very specific bounds. So B has bounds n max, A goes from 2 to n max, and C goes from 1 to n max minus 1. And D is just of size n max, X is of size n max, because those are just vectors with the full size. And then it goes on and it does some working of its own. You don't have to worry too much at all about what it's actually doing here. If you like, you can just trust that this is correctly doing the work to solve what X is. What are the values of X that solve that equation AX equals D? Does my explanation so far make sense of what this is at least trying to do? You don't need to worry too much, but if you do care about it, please let me know. As I say, everything that's going on here, you can just trust that this is doing the work to solve that problem. But what we want to do is just maybe write a module. So we've got this code, and it's right here in exercise. Yeah, exactly what I was showing just now. Here's all this code, and it's all here in the program. So I think it would be a nice little exercise. We can just spend maybe 10 minutes on this. If everyone can perhaps just try themselves to take all of the workings here, all of this, and try to put it into its own subroutine in a module. So you don't have to worry about what this is actually doing. Just take the code as it is. Think about, okay, how do I put this into a subroutine that looks like this? It takes in the vectors B, A, and C. The right-hand side is equivalent to the vector D. And then it returns the solution X. So let's maybe take until about 25 past. So that's a little bit under 10 minutes. See if you can quickly do that. For the most part, this will be a matter of copying and pasting. So if everyone has a little go at this, if anything here just doesn't make sense, please do say in the chat, and I'll try to help you out. Otherwise, though, let's spend about 10 minutes working on this and seeing if everyone can take this code, package it up into a subroutine, and package that subroutine up into a module. Okay, I will stop sharing and see what I can do myself in that time. And yeah, please do shout if anyone needs any help on this. So something just to point out for everyone, when you're doing the dummy arguments in your subroutine, you should be trying, if you can, to make them assumed shape. You don't have to worry too much about doing the checks here. You do that if you were making production codes. Here you can be a little bit quick about it and skip out the checks on L bound and U bound and just assume it's correct for now. But at least try to make the templates do it that way. Okay, how's everyone doing? Are you happy to look at the solution, or would you like a little bit more time? We could go another 5 minutes, perhaps, if people would like that. If anyone has any opinions, please just say more time, or go now, or whatever in the chat, and we'll go with what people say. Okay, I'm not seeing anyone with any strong opinions. What I'll do then is I'll share my screen. I'm actually not quite at the end myself, so I imagine no one else is, but I'll show where I'm at, and you can compare it to where you are, and we'll just go through the last few parts together. Let me share my screen again. So that should be popping up in just a second. So here's what I've got. On the left here, I have the module that I've set up partially. I'm getting close to the end. Module solver, I'm using ISO Fortran env inside it, and then I've got my implicit none, of course, because that's what I always need to do. And then there was this parameter my kind, which was being used to ensure that everything was the same kind, and I've just put that in here as a module parameter. Then I've got contains subroutine try diagonal solve. This has that same set of dummy arguments that we saw on the on the material there. I've just copied and pasted that. And everything in here, almost entirely, is just a copy and paste of what's in the code, which I still haven't quite finished editing on the right from the exercise. So I've copied and pasted all of this, all of the actual workings. I don't need to know at all about how this does its thing. I've just copied and pasted across. The only thing that I've done is I've said what nmax is here, is to be the u-bound of b, because I didn't know that. And that's because I've just added some dummy argument declarations here. And these are just for all of these parameters. BAC, the right-hand side, so BAC are the vectors making up that big matrix. C is the right-hand side, and X is the unknown vector which we're trying to solve for. W and I we had before on the right-hand side. I've just taken those straight across. I think I've actually deleted them from here. Yes, I think I have. I've already deleted those. And then nmax I've added because we need to know how far to go. So I took care here, took care to say that B starts at index 1, which was the case here. A starts at index 2, which was the case here. C starts at 1 again, and RHS and X both also start at 1. Remember, RHS corresponds to D here. And then all of this is just copied and pasted. I still need to finish off the module, so the subroutine. So I'll just do end subroutine solver. Was it? No, tri-diagonal solver. No, tri-diagonal solve, I think it was. So I think that's right, hopefully. Now, in the program, what do I need to do here? Well, let's not bother with my kind. We will use nmax, although it's a different nmax from the one that's used inside the module. That's a local nmax. They're not the same thing. They're different from one another. This nmax only exists in the subroutine. This nmax here only exists in the program. Then I declare these. We do need to declare these here because that's our data that we're working with. But then I'm going to just delete all of these. So the program now is using the module, implicit spanning, setting up the integer parameter, which is the size of the problem, and then just declaring everything. It's not doing anything more complex than that. We do want it to call our solver. So let's have it just call tri-diagonal solve, and we'll give it what are the arguments it needs. Its actual arguments should be B, A, and C. So they're called the same thing. That's just coincidence. The right-hand side is called D here. So we'll pass D through to it, and then we'll get our solution vector back, which is X. What we might actually also do, I might actually, let me delete that, and I'll put it there. So yeah, so I'm just printing the solution out here. So all of the work now should be taking place in the module in this subroutine, tri-diagonal solve. While the program itself is doing nothing but the setup, defining what the problem is, and then calling the solver to do that. So now, if I try to compile that, let's give that a go. What did I call it? Module and pro and exercise. Let's see. Incompatible ranks 0 and 1. And this, what have I done wrong? I've done something wrong in my module. Maybe I think maybe size. I think I'll use size instead here. It should do the same thing. Okay, and then I've just missed out. So when I copied and pasted the code to do the work, I've missed out here that this D should be changed to RHS. So I just need to find that, and that's why it's here, because that's called RHS. That's the name of the dummy argument. Write quit, try to compile, try to run, and hopefully that's working. How does that look for everyone? Does what I've just done there make sense? This is a little bit of a bigger project than I think the ones we've done before. So if anything there doesn't make sense, please do say so. Thumbs up, thank you. Okay. Anyone else? Anyone have any problems? If you do have any problems with any of this and don't want to put in the main chat, you can send me a direct message as well. Please do feel happy to do that. Go ahead if you would rather just chat directly to me about something that's not working for you. Okay, with a single, so yeah, with that thumbs up, I'll assume then that everyone is happy with this, and we'll move on for now then. So I think that's us, hopefully all happy with that. We'll move on past our break. And okay, this should be a little bit lighter now. We may not bother too much with these exercises. I'm not sure. I think this is fairly self-explanatory. We'll try and breeze on past this to more useful things, I think. So leaving behind complex things like arrays and numbers and just talking about strings again, you can do certain operations on strings that would work as you would expect when you remember that characters are internally to the code just treated as ASCII sequences. So each character has an integer that is used to represent it at the machine level. And that means that you're able to do things like capital A is less than B evaluates as true, because in the ASCII sequence, the value of A is capital A is less than lowercase b. You can actually find what those characters are. You can convert back and forth between them using the intrinsic functions IACHAR and ACHAR. So IACHAR converts from character to the integer. So uppercase A converts to the value 65, and if you go the other way, then that converts 65 in this case back to the character uppercase A. You can also do direct comparison of character variables, in which case they'll go left to right, just compare character by character. If a difference is found, then it will come back as false. If it goes the whole way through without finding any difference, then it will come back as true. And yeah, it will just pad with blanks. Fortran has this thing where it always pads with blanks that aren't actually the same as white spaces. It's good to remember that when Fortran pads with blanks, it's an empty spot where it's saying the spot exists, but there isn't actually any character in there, not even space. Something that's probably familiar to people, again, yeah, the len intrinsic function of your Python into Python at all, that will look very familiar to you. Len can be used to find out how long a character variable is, and you can do len trim to do the same thing but remove any blanks from it. Often what you want to do is you'll very often be working with character variables which are longer than you expect. So if you're expecting some input field to be however many, to be n characters long, you might define the actual variable to hold it to be 2n, just to give some extra space in case it's needed. Then when the time comes to actually use it, you want to get rid of those trailing blanks, and you would use the trim intrinsic to do that. So for example, maybe you're working and you've got a file stub, so the bit of the name in front of the dot and then the extension, and this is going to be a file that you're working with. You would do file name and you would do trim file stub. Double slash is the concatenation operator. Remember, we saw that yesterday afternoon. Concatenate with dot, concatenate with the trimmed extension. You can also do things like this. So you can loop through the whole string, excluding the blanks by putting trim onto len trim, and then say that if a particular character in the string, so you'd use this operator to do that, string, and it does look a lot like a array array section operator. N to N, we're just saying just this single character section of string. If it equals to A, then we'll increment some count. But you could do other things. There is an example down below where you could do something involving this, where you change every character between uppercase and lowercase. I think we'll skip that. I'm not sure it's too instructive for us just now. But you can do things like this if it's helpful. And you do have to have that colon mandatory in a substring reference. So you can't just do string 2. You would do string 2 colon 2. It's always expecting some range within that. If you want a range of a single character, you just do number colon number. But you can't do it without the colon and the second value here. There are other intrinsic functions. I think I did say yesterday, but actually did I? But Fortran is a very big language compared to some. The actual core standard of the language is a lot bigger than most other languages out there. So it does provide a lot of these helper functions, a lot of these helper intrinsics. It can be sometimes a little bit difficult, at least, to remember which of them are out there, which ones are out there to help you. So that's when looking at the docs, of course, is helpful. But they're all in there. You don't have to import or use anything to use them. They're intrinsic to the core Fortran language standards. Yes, what you might want to do as well, so you can defer lengths of strings, and this is actually, and you can see there's the word allocatable here. This makes it a little bit like working with an allocatable array. The allocations happen in the background. We don't do them ourselves, but if you create a string like this, we saw using a star before. When we created a string with the star, we were saying to the compiler, essentially, we can't be bothered to count how many characters are needed for the len. Just work it out yourself. We're saying to the compiler, you work out how long our string is going to be, because we're doing its initial allocation here, and use that. But what we can do is we can defer it. So if we know that we want a string, but we don't know yet how long it needs to be, we can give it the colon here for its len and make it allocatable. And then later on, we can just assign to it. And at this point, in the runtime, it will allocate it in the memory, and then give it and then assign to it the value ABCD. If we then give it another assignation, it will deallocate it, then reallocate it at the new length and put the new value into it. If we want, we could then do this too. We could do string colon equals blank. And what this will do is it will keep the same allocation as this, which is 7 characters, but it will just set all of them to blank. So it's the same memory. It's not going to deallocate and reallocate again. It's using the same allocation, but just set it all to the equivalent of nothing. So you can do this, and the runtime then, as it says here, will keep track of that bookkeeping. This is generally a good way of doing it, just to avoid those trailing blanks. So this is something which you do definitely only see in newer Fortran, older Fortran, even I think in 95 and 90 possibly. I don't think it was possible to do this. I could be wrong, but at least this wasn't common. I don't know, before maybe 10, 15-ish years ago. I don't think I ever saw anything like this while I was an undergraduate or a PhD student. So this is fairly new. And to be honest, you may already be seeing hints of this, but Fortran is not the best language in the world at doing string manipulation. For that, you definitely want something like Python. Fortran is a little bit clunky around strings, but at least allowing for deferred length strings gives us a little bit of help. It makes it just a little bit easier. It was very painful before. What we can do as well, if we want to create a deferred length string, just the same way, but we want to, for whatever reason, allocate it, but without doing the assign to it, as we've done here, we can manually do that do that allocation like this. We just put inside the allocate brackets character len mylen string. So once we know what the value needs to be, we can by hand force that allocation to take place. And they should be automatically deallocated, as with allocatable arrays, in the same way. Once they go out of scope, they should be. Of course, I guess things can go wrong, but they should be automatically deallocated, and just exactly as you would expect. Something a little bit interesting to think about is, what if we want an array of strings? So you can define a fixed length parameter. So let's say we want to create a parameter. Then here we're using star. So we're saying to the compiler, create a constant string of length needed to hold Sunday, which is six characters. So it's going to create the parameter day of len 6 holding Sunday. What you could then do is this: character len equals star dimension 7 parameter days. And what we're now saying is, let's create a whole array of size 7 of strings which are going to hold those days of the week. And we can just take a quick look at this at example 3.f90. So let's go down into 11 character strings. And was it example 3? So let's just take a quick look at example 3.f90. Here we have it. Character len star dimension 7 parameter days. So we're creating an array, and what we might expect is that it's going to create this array and say that each of the strings in that array are going to hold each of those days of the week. And then we're going to print out each of the days in that array, its length and its trimmed length. So let's just quickly try and run that. It's ftn example 3.f90, and it doesn't like it. So we immediately get some errors, different character lengths. So what's going on? What's going on is that it doesn't like it. It wants each of those in the array to be the same, essentially. So what you could do is you could pad the lengths of each array element to be the same length. So by that we mean we would, for example, say, what's the longest one? Saturday. Well, we could just add some extra spaces on the end here. Sorry, Wednesday. So we put 3 extra spaces. We'd have 3 extra spaces there. That would work, but I'll just quit without saving. But what's a little bit more intuitive is to do this: character len equals 9. So if we put that in the front of that array right here. It's going to look a little bit long, but that's still okay, I think. Yes, that's fine. So we're now saying that each of these in here is now going to be a character of length 9. So we can write these out and it will automatically do the padding for us and then store it in an array of characters of the correct length. So if we now write quit and try to compile that, that now builds a.out, and we can see that it's created an array. Each of those strings within the array is length 9 because of what we did here. We told the compiler in no uncertain terms, each of these items is to be a length 9 string, and it's done that, but the trimmed length of each is different. So that's a little bit strange. It's just part of the way that strings work. And as I say, Python, Fortran and strings are not exactly a match made in heaven. If anyone were looking to write a code specifically to work with strings, I would certainly not recommend Fortran to them. Fortran's strengths are in its mathematical abilities, its ease of using arrays, not in its ease of use with strings. You can have character variables with intent in procedures as well. So, for example, I think this should just be arg1, not carg1. I think that's a typo. I'll have to fix that. Sorry. So, if you have a subroutine, some character operation, and an argument 1, which we'll just call arg1, you can give it len star, and that just means that whatever, again, just as before, essentially, whatever size it needs, it will be given. It's intent in, so it just knows that it's not going to touch it. And if you're going to be doing in out and the length isn't going to change, you can do the same thing. If, however, you were going to change its size, then you need to take a different approach, and that would look more like this. File name would be what you would be using here, and instead you would use the colon operator and make it allocatable. So you're now switching to a deferred length string. So now what you're doing is you're again allowing the runtime to deallocate the old string, and then allocate again with the new length under the same name, and then pass that back as the result or as the intent out argument in a subroutine. So I hope that makes sense. This isn't too tricky, I don't think. It's just a little bit weird and a little bit. It just needs a little bit of thought, but I don't think this is as awkward, well, as dangerous, let's say, as array bounds when you're doing assumed shape. So it's a little bit awkward. It's a little bit ugly, perhaps. It doesn't quite work nicely, but at least it isn't difficult. So I hope that makes sense to everyone. So there is an exercise here. I really don't think it's worth us spending time doing this. If you're interested, please do take a look at it. Please do get in touch with me if you have any questions. But this is fairly simple. I think with the exercises we've been doing so far, everyone should find this fairly simple. It's just a matter of doing this maths here, essentially converting between integer and characters and adding values to move them between uppercase and lowercase. Again, that's something which in other languages it would be very, very easy indeed. Not quite so simple in Fortran, unfortunately. Moving on to formats and edit descriptors, we'll maybe go through this actually, shall we maybe have a quick break? I think we might have, let's just actually take a quick 10-minute break. Yep, we'll just have a 10-minute break here, given the time. We're still aiming to end at 4. I don't want to keep anyone any longer than we said we would. So let's just take 10 minutes now and come back at 3 o'clock, and then we'll move on with this and see what we can manage before 4 o'clock. So 10 minutes time, and I'll see you back then. Okay, see you in a wee bit. Okay, hi again, everyone. Welcome back. Let me get rid of the message. Just had a question from someone asking, why doesn't changing character len equals star? Actually, let me share my screen again so this makes a little bit more sense. Let's bring it back. Let's head back to that. Yeah, so why doesn't changing character len equals star, the first part of the line of variable, when variable is defined to len equals 9, just here, not work? Why do we have to redefine character len equals 9 once we are within the array? Well, let's just try that out. Right? Let's take a look. Vim example 3. So what we could try is this. Let's see. Let's just try changing this to 9. And if I ftn that, we get an error again. So the issue is in the way that it's constructing the array here. It's saying, how can I explain this? What we're saying is that every character that it's every string that it's expecting to store here is 9 characters long. But the problem is once we get into the constructor itself, at this point we're passing string literals into it. So these are literal constants, if you like, and they have different lengths. So we're saying to it now, if you like, set aside 9 bytes of memory, or well, space for 9 characters for each, and into each of them put each of these. Into each spot put one of these strings. And for some of them that will work, and for some of them it won't work, because these ones are too short. If we had just done a star as we had before, so if we had, oh, I've already lost it. That's annoying. If we'd done this, then we're allowing it to individually expand them, if you like. But up here, this part, this should actually now itself compile. Yes, it does. It's a sort of disconnect, I suppose you might call it. Here it's saying everything has to be length equals 9. And in here it's saying this is 6, this is 6. And the compiler, the language isn't flexible enough in how it deals with strings there to realize that what's out here means that it can just expand these. More than that, I'm not sure I can explain exactly why that disconnect occurs. But that's essentially what's happening. So the reason for that is some depth of the language I am not myself certain of. But there's that disconnect between the length here and the length here, where the length here is not enough information for the compiler to realize it's allowed to expand to pad with blanks everything on the inside. What's needed is that extra little bit of information inside the array constructor, where here that I've highlighted, where we say each of these is a character of length 9, and you're allowed to pad them. So now within within just this bit of syntax itself, within the square brackets, the compiler can now go, oh, okay, each of these is a string of length 9. Let's just pad them, and then that feeds back into the outer declaration of the array. So I hope that somewhat answers the question. It's not complete, but okay, great, thank you. I wish I could say why there is this disconnect. It's going to be something I would imagine fairly low level in the parser of the language, where this part is probably treated as being completely semantically separate from this part, and it cannot match up between them what is going on. So it just needs an extra little bit of help. Okay, so we've got about an hour left, so let's try and get through what we can today. So we were working on formats and edit descriptors. This may not take too long too. So again, this is just working with strings. So far, if we think way back to the beginning, we introduced print and write. We haven't said anything more about how to get input. But we did mention that input unit was available via use ISO Fortran env. We've actually changed the syntax here a little bit. This is a little bit more modern again. Use : : This is optional. Still pretty uncommon to see, but this is cutting edge Fortran style now. I personally wouldn't even put these 2 colons in, but just so you're aware, that's possible. That's something that you might see. But anyway, if we use ISO Fortran env, we get access to input unit, and what we can do, we can just say read unit equals input unit format equals star. So this is free format again, the same free format that we used with print star and write unit whatever format equals star. And then we just provide a comma separated list of the variables that we want to read. But there is a little bit of a difference in that write, you can put expressions in there, you can put variables, you can put constants, you can put literals in there. When you read, everything that goes in your list here has to be a variable which you're allowed to write to, which is going to store those values which come in from the keyboard in this case. The input unit that comes from ISO Fortran above is typically the keyboard, or the screen if you want to call it for interactive use. But you can change this. So again, this is just one input unit. So if you use input units, you're talking about the keyboard, but you can provide it with a different unit if you want, and that would very possibly be a file. Remember, they're just handles to whatever we happen to want. Something that's worth thinking about then, that's what we'll be talking about for this lesson here, is how to format our input and output. So we've been using star everywhere until now, but you can change that. So here's one simple example: print, and then rather than star, we've got inside quote marks, open bracket, a, close bracket, and then we print a string. So this is what a format specifier looks like. It's a string. It's a string itself, which is why we put it in quote marks, and then it goes inside brackets within that. And whatever goes in the middle is your format specifier. A, like this, means that the format is specifying a string, which in this case is actually the text a string. But you can also use a character variable to refer to that. So in this case, my format is a string, which we've declared somewhere, and we filled it up with something like open bracket, a close bracket. and then we can just use that wherever we want to use that format in our output. Something else that you can do when you do a write is you can skip the format altogether. And in that case, what you're doing is you're doing something called unformatted output. And this is not done really very much anymore. It's the oldest way, I think, of doing binary input output in Fortran. So almost a raw dump to file of your of data. And it's a little bit it's a little bit it's a little bit finicky in how it works, in that every write that you do to the file has to be matched to a read in terms of the numbers. So you can skip between them. You have to match them, otherwise it gets out of sync. I think this is possibly possibly a holdover from the old tape storage days. But it's a little bit finicky. The first big code I used in my PhD relied completely on unformatted I/O, and it does work, but it's tricky. It's very difficult to get working with anything that isn't Fortran as well. It's very, very hard to read into other languages like Python or C, because it has this extra record thing built into it. It's not really recommended. So nowadays, if anyone were wanting to do other types of binary input output, you probably want to use something like HDF5 instead. This is very much old Fortran now, not modern at all. But formatted output is nice and simple in comparison. It's just text, which we're writing to the screen or to file or wherever we need it to go. So what can we put inside here? So we've seen one little example, which is lowercase a. Lowercase a just means that the thing that's going to be written is a string. But what if we want to output numbers? Of course, that's what we really care about in Fortran. So a format consists, this is very formally put, consists of a comma-separated list of edit descriptors enclosed in parentheses, and those edit descriptors determine how the internal representation is converted to characters, which can be displayed on your screen or in your text file. It's very long. There are lots of options available. I'm sure a lot of you will have seen similar things in C and the like. It works broadly in a similar way to that. So it's not too difficult to move between different languages. It's just a matter of sometimes of remembering the different symbols used. But the way that they work is very similar to one another. So if you want to print integers, you can just do the character I, and then W here is to be an integer value, which is how many how wide do you want the field to be. F W point D, floating point numbers of total width D, and D decimal place characters after the decimal place. E gives you scientific notation, and you can do A again, as we did up here. But if you give it a width, you can specify how many characters you want that to be. So the width is everything. So you need to make sure that when you give it a width, you make sure that it's wide enough to contain anything that isn't a number. So that includes any signs, decimal points, or exponents, the character E. If you don't make it wide enough, typically what happens is you just get stars printed out, and that can be a little bit unhelpful sometimes if you actually want some information, particularly if it's something that's been running for a long time. What you don't want is to get a load of stars printed out and tell you nothing at all helpful from your run. When you use those in the format specifier like this, you need to make sure that they're positioned correctly. So here you can have print I10, IVAR, F10.3 AVAR, E10.3 AVAR. So this is fairly simple. I10 means that we're going to print out the value 40 with 8 leading spaces because we've said that it needs to be a width of 10. F10.3 floating point 40.000 because we said we want three decimal places with a total width of 10. That means we're going to have 4 leading spaces. Scientific notation means that we're going to start with 0 point and then the number with here 3 decimal places plus 0.2 is the power on that. And again, we gave it 10, a total width of 10 for 1 leading space. How many digits you get in the exponent depends on how big it is. It will automatically go up to a wider field if it needs to go beyond 99. Personally, I find ES to be more useful than me. Beginning with 0 point, I mean, I'm from an astrophysics background, and at least in our field, we always began with a single significant figure, and then went on with that. You can also use EN for an engineering edit descriptor, but this means that your exponents have to be factors of 3 for the standard SI prefixes. And you can also add a number for the exponent itself if you do need to. For the characters, you can do something else. You can just say AVAR, so you can put a string literal inside it. I think this is, some people still do this. This is a question of style. Personally, I wouldn't do this, and I would just put a string as part of the list. But you can put a string in there, so you just enclose this in quote marks inside the edit descriptor, and this will just print out, this is the results colon AVAR using E14.7 as the format. Then to control them, you can use some extra helpful ones. The only two that we're really going to bother with here are X for spaces or blanks. You can put a number in front of that as well. So if you wanted to have two spaces between IVAR and AVAR, you would just write 2X, for example. And if you want to actually give a plus sign, you can put SP in front. So you can put the SP there, and that will add a sign in front of whatever number you have. Let's just quickly take a look at this. So example 1.f90, let's take a look at that code. So that's in section 12. Let's take a quick look at example 1.f90. We're printing out a lot of things. We've got 4 variables, an integer, a logical, a real, and a character. And then we print them out with their various specifiers. Some work, some don't work. Let's quickly compile that and see what happens. So there are some which work, and I mentioned stars earlier. We can see some things are breaking here. Some of the specifiers have not been allowed a large enough width. What's the result? What's the solution? Well, we'll take a look at that. It's fairly obvious which ones are wrong. You can just see various examples. If you're anything like me, probably what you would do in any language at all is you would find probably a few go-to formats which work for you for various data types, and then reuse those all the time. But the ones which didn't work were I1 and F10.3. So if we take a look at those, I1 and F10.3, these two didn't work. So I1, IVAR. What is IVAR? IVAR is 40. The problem is that we've only allowed it a single character. So let's just try changing that to I2 and seeing, does that fix that? Compile and run, and it still doesn't work. Ah, because it's minus 40. That's my fault. So let's make it I3 and try that. And now we get all three characters. So I1 simply wasn't big enough. So if it isn't big enough, as I said earlier, it just prints stars at you. What was the other one that didn't work? F10.3 AVAR. AVAR is huge. So let's maybe just do this. We can do print star AVAR. Huge, by the way, is an intrinsic function which returns the largest possible value that you're allowed to store based on the type of what you give it. So AVAR, we say, is a real 64. So what we're doing here is we're saying that AVAR is going to store the largest possible number that it is able to store. Remember I said floating point numbers do not have infinite range and precision. So here we can see that the largest possible number that can be stored in a 64-bit real is this. That's pretty big. And we tried to print it out with F10.3, which is clearly not enough. So what do we want to do? Well, we could just make it really big. Let's make it what do we want? What would be a good one? Let's think. Make it 30.20. This will be more than big enough. This will be huge. Oh, still not enough. Of course not. Of course not, as it goes all the way on. So this is, yeah, no, of course, yes. The issue here is that it's got 10 to the power of 308. So we actually need to make that really big. Will this even work? I'm not entirely sure. Let's make it 350 character. 350. Let's see what this looks like. This is a bit over the top. I'm not convinced this will work. Okay, it does actually work. Although it tries to. So this has actually printed it out. It has printed out this huge number with 308 places after it. Of course, after 2157, this is the only part it's actually storing. Everything after here is essentially noise, if you like, from the binary conversion. So that's why you wouldn't really use an F to store a huge number like this. Much better would be something like this, format E10.3. Store it as a scientific type number. Okay, does that make sense to everyone so far? I've gone through this fairly quickly, but I don't think this is too difficult. So I hope that's not been confusing for anyone. All good, I think. Okay, great. Okay. I don't think there's a great deal to do here. So repeat counts. So things that you can do to make your life a little bit easier are to, if you like, put parts of your format specifier inside brackets like this here. And then if you put a number in front of them, it just means repeat everything within those brackets however many times. So this just means do 2x E14.7 4 times. Why are we doing that? Well, we've got 4 elements inside this array A. So we're just printing out 2 spaces and then the number in scientific format four times, and that just makes it easy for you. You can then put another comma here, have more format specifiers follow on from it. It just saves you busy work essentially, and makes things a little bit easier for you to work with. Complex variables are fairly simple, just the same way as we used real kinds to describe complex numbers, complex variables. When you print them, you just treat them as two reals, and they do not have to have the same edit descriptor either. You can use different ones if you are expecting that you want to that you'll want to represent the real and imaginary parts in different ways. If you want to print out logicals, then you can use L, and we actually did see this here. We had L10 for F, which we used in our code. A safe width for that would be 7, so portable, because this does depend on compiler. You want to make sure that they're able to print false, so .false dot. But some implementations will only produce an F. So I'm using plugenv GNU. If I do module node plugenv cray, that might be interesting. Do we see anything different? Not actually, no. Okay, so these both do it in the same way. So both the Cray and Fortran compilers both just produce F. Maybe the PGI or an NVIDIA compiler produce .false dot or .true dot. You can't be sure, I guess, depending on what happens. So you might want to just give them 7 characters to make sure that you've got space. This will be a bit more helpful, perhaps. We will actually do, we'll not bother with this, I don't think, however. But something that will be useful, perhaps, for an exercise that I think we'll try tomorrow will be advanced no. So when you're writing to anything at all, whether it's the screen or a file, if you want, you can tell it to not move on to the next line. So everything that we've done so far in this code, we didn't tell it anything about going on to a new line. There's a sort of implicit new line in each of these. It always moves on to the next line. But if you're using write rather than print, and also if you're using a format here rather than just star for the format, you can give it the extra optional argument advance and tell it no, where by default it would be yes, and that means do not do that carriage return to the next line. So if you're doing something where you want someone to do this, input an integer and then have them enter their input on the same line without it going on to the next line, just put advance equals no. This will be a bit more useful, as I say. This can be helpful if you're doing things like printing arrays. This is, as I say, a hint for an exercise we'll probably do. But if you're looping through an array, say, and you're printing to the same line, perhaps a row of the array, if you're envisioning it as a matrix, you want to be able to print each element and then move on to the next one, move on to the next element, move on to the next element. And then when you're at the final element of the row, then you would, and only then would you add advance. So that's just a little hint for the exercise that we might try tomorrow. I don't think we'll have time for it today. And finally, statements, labels. So this is something that you might see very often, very often in older code. Fortran 77 loved doing this, and some people decided to take it with them into modern Fortran, so you do still see it. But statement labels are a little bit like when we put names in front of if statements and do loops. It's the same kind of concept. If the line just begins with a number, an integer, here it's 100, what we're doing is we're giving the statement on that line a label. And then whenever we want, we can use that label to refer to it. So we aren't saying that there's anything here to be executed. If you like, it's almost like a macro sort of, where we're just saying format i3 f14.7 can be referred to with the integer 100, and then in other places you would reference that format equals 100 in this write statement, and the compiler would sort of copy and paste format into here. It works, and for old Fortran it was necessary for some strange reasons I don't entirely grasp. My PhD student, sorry, my PhD supervisor once tried to explain to me, and I got a little bit lost. But you don't really see this anymore, and it can be very, very confusing. The code I was working with was doing this, and the formats and the writes using them were, I think, in at least a couple of cases, literal thousands of lines apart. This code had some huge subroutines, and you really had to go hunting for the bits of code that were being used in various places. It really doesn't help at all if you see, oh, I'm writing IA, IB, and C out. What's the format? And then you go, oh, okay, this is 2,500 lines further down. They can still be used, so yeah, we'll see in error handling in just a second that they can still be used, but it's more uncommon now, and certainly in this context, I wouldn't do this myself in modern code. I would just put the format in there as a string within the right statement itself, or if I wanted to reuse it, I would actually just store it in a string variable as we do here, and just use it like that instead. Okay, so breeze through that again, and there is a challenge here again. I really don't think I'm not sure it's worth us spending time on this again, given we're at the end of the second day. If you're interested, I'd say take a little look. It shouldn't take you too long, but I think right now it's probably more important for us to just move on to external files. Then we'll probably end up starting tomorrow with name lists, which isn't too long. So let's just carry on for now, and tomorrow we'll spend some time doing some of the bigger exercises. So operations on external files, this is of course very important. We want to make sure we're able to get data from files and then put our results into them. I mentioned HDF5 or libraries like that for doing binary input-output are certainly something you would want to consider if you are really going to be writing large amounts of data to file. But for smaller amounts of text-based information, you could do it entirely in Fortran, just like this. So we've been mentioning unit numbers a lot, how they're handles to various sources of input and destinations of output, and we open them using the open function. For that, we need to have an integer available. So this is the newer way of doing it. I'm just going to talk about this way, and then I might mention the older way of doing it, which causes some problems as well. So let's imagine that we've got an integer called my unit. What we would then do is call the open function, and we tell it to open file name.dat form equals formatted, because we're going to be writing formatted data to it. Action equals write, status equals new. So this is sort of helping the operating system on a bit, and helping the compiler, if it sees that we're treating the file that we've just opened in a way that doesn't match what our action here was, it will tell us off. If we try to write to a read-only file, that's a good thing. It means that we're going down the wrong tracks. Status new means that it's going to open a file where none exists. You can also have status old to say that the file should already be there. And then there's this bit at the beginning. So this is where the unit comes into it. And what we're saying here is new unit equals my unit. When we do this, we give it our integer, an integer variable that we've already declared, and we pass it through with this optional argument new unit, and that's telling it to find a unit which doesn't already exist, so one which isn't already being used, and to store it inside there. Because remember, units are just integers, they're just numbers. We did see that yesterday when we were looking at the input unit, error unit, output unit, with the two different compilers, and we saw that on Cray they were, what were they, 100 and 101. On Fortran they were 0, 5, and 6, I think. Remember that they're all just integer numbers, and we don't necessarily know which ones are safe to use or not. But what we can do is this: we can just say open new unit equals my unit, and it will then just take this and it will store any number that the runtime determines is safe to use inside there. We don't have to ever think about it. So when open returns to us again, and we're back down here ready to write, we know that whatever number is inside my unit, it's a number that's safe to use because it doesn't refer to standard output or something. It refers to only the file that we have just opened here. And at that point, we can run write statements and give it unit equals my unit, and it will write whatever we tell it to that file. So this is a much newer way of doing it. It's much safer. You could, if you wanted, just put numbers in here. Again, a code I used when I was a PhD student had been written to do that because it was from the 80s or something. I think it was from the mid 80s. And it made parallel runs very difficult for some reasons I might talk about tomorrow when we get to that. So yes, this is what you should always be aiming to do now. When you're opening a file, do new unit equals a variable, and then you know that variable is a safe, contains a safe unit handle to use to that file. You can do the same thing for read. In this case, what you're saying is that you're going to be opening a unit again, opening a file again, storing the unit in my unit, just the same as before. Form equals formatted again. Action, we're now saying that we want to read to it. So if we start writing to it, the compiler will complain to us, as it should do. And we can also tell it status equals old. Status equals old means that if at the point it goes to open it, it doesn't find it in the file system. At runtime, we will get an error. There is actually another. Do we talk about replace here? I want to just mention it if not. Okay. Okay, we do come down. Yeah, okay, it's just below. So new unit. So yeah, only Fortran 2008, but this is definitely the best way to do it. So these arguments, I think it's worthwhile mentioning. Old, new, replace, scratch, or unknown. Old means that it has to be there, otherwise you'll get an error. New says that when you open the file, it will be created from nothing, and if it already exists, you'll get an error, in which case you need to delete it first and then rerun the code. Replace means that it will open it again, and if it's already there, it will be overwritten by whatever you're now going to write. Scratch means that it's a temporary file, so it will just create something, and then when you close it again, it will be RM'd, basically. And unknown just means it's dependent on the system. It's sort of going to an unknown default, if you like. I personally would always just use one of these, and it should always be fairly obvious which one you want to use. When you finish using it, I didn't mention close. When you finish, you just run close unit equals whatever, and status equals keep, which is the default, which means don't delete it. If you choose scratch, then you get delete on it instead. You can do inquire, so that's a way of checking whether either a unit number or a file exists. There are lots of things you can do. This is sort of like the OS type stuff that's you're able to do in Python. So there is some helpful stuff here. If you just want to check that a file exists, you can run it, and then your logical that you pass to it exists here will come back true or false, depending on whether that file name .dat is sitting there or not. You can also use an internal file. So this definitely looks a little bit strange. This would be a case when you want to write some kind of formatted output, if you like, into a string. So this is strange in that we call it an internal file. It works a little bit like sprintf. It generates a new string from components, literals, and variables. This is definitely not as nice as Python. You can hopefully see. But if you imagine we wanted to create a string of our own that contained some formatted value, we would do it like this, but we would put read into it, and we would then read the value of eyeball with that format into the buffer string. The main case I've ever seen for using this, and again, this could be helpful for some of the exercises you do tomorrow, would be if you want to create a format string at runtime. So you can imagine, I mentioned earlier on, printing out arrays. You can imagine, actually, you could print out a whole row or column of an array if you had the correct format for it. How do you create the correct format? Well, maybe you know beforehand how big the array is, but if you don't, you maybe need to be able to write at runtime a correct format string for it that changes depending on what its size is. And in that case, you could do this to create that format string at runtime and have it adapt to the size of the array. Array handling is definitely, again, it's just a little bit old and clunky in Fortran. It works, and there's no formal mechanism for it, but you can somewhat deal with errors when working with files, and it involves these statements labels again, 999 here. So what's happening here? This is definitely a little bit different from any subroutine that we've seen before. Let's imagine that we've got a unit that we want to read from, and we want to pass an error code back. Excuse me. And then so we say that my unit is an intent integer. The error code that we're going to pass back out to whatever is calling this subroutine is an integer intent out. And it might even come with a message along the way. And then when we do the read from the file, we can do everything as normal, but we can give it these two optional arguments, error and IO message. And what will happen then is that if this exits OK with no errors, it will just carry on below, down to here, and it will set IError equals to 0, and then it will return. Remember, return is a statement that says, at this point, leave the current procedure and jump back out again to whatever was calling us. So if you go down here, everything was fine, set the error to 0, which is always taken to mean OK, and leave. If, however, things went wrong, then we've got error equals 999. And what this means is that if you do hit an error while doing this read, jump to statement 999. What is statement 999? It's continue. Continue in the context of a do loop used to mean sort of the same thing as cycle. Now it just means a sort of no op, if you like. It just means carry on. It will also store a message in this string, MSG, message, but maybe hopefully this is a little bit implementation dependent, but it will hopefully tell us something about what actually happened, what actually went wrong there. So we're going to jump down to 999 and just start from here. So we're below that return. It then sets the IError to -1, prints the contents, trimming it of that message, and then returns again. So we'll be coming back out again with IError either equals to 0 or equal to -1. So you can hopefully see how this works. You can also probably see that it's just a little bit clunky. This is definitely, I think, something where old style Fortran is still kind of, it still hasn't been updated, I guess, in any way. This is very, very old style code. The reason that we're doing it here is because there isn't at least yet any better way of doing this. It's not very nice because this is essentially functioning as a go-to, which I definitely do not like, because just looking at this code here, you can't see anything here in this code itself to say how that logic works. All of the logic is coming from this here. And I think that's not very clear myself. I think that is not entirely transparent about how this logic works at first glance. You can take a look at it and then you'll go, oh, okay, yes, I see. But I think being able to use ifs or cases or something to handle the different outcomes, or just to try and to try something and to catch the error would probably be preferable. That's probably something you're used to if you're coming from other languages, but at the moment, at least, that's not something that Fortran can actually do. So we have to be able to do this if we want to be able to handle those errors. It's not nice, in my opinion at least, but it does at least work. Um, and yes, and really the same thing does occur when you open and close as well. So you can, if there's something that's gone wrong while opening things, you know, this could even come down to something like running out of space in the file system. You should get back some kind of message to tell you. You can also get back this IOStat code, which again tells you a little bit about what's happened. If it's 0 on success or positive if there's been an error. Um, but what will generally happen is that if you generally don't provide these and you hit an error instead, what will probably happen is you'll just get a crash of your program. If you want to try and exit gracefully, as they say, if you want to try and actually handle the errors and maybe print out some useful information for the user, you would need to provide at least one of these and then work out how to deal with that. And very similarly, it works with write, and there is something a little bit different here, which is that you can have an end label as well. And what this does is it tells the program what to do if it hits end of file. That can be helpful if you're reading some input, say, and you don't actually know how long it is. You can just put an end in here, and again, you give it a statement label, and if it hits end of file, it will just jump to wherever you happen to put that in a sort of go to like fashion. Error, it can be the same if you want, and you can get two different values for IOStat. You can get negative values for end of record or end of file. End of record, this is really if you're dealing with unformatted data. So it's not probably, it's hopefully this is never going to be too actually useful for anyone here, because hopefully none of you ever have to use Fortran unformatted IO. But if you do, you can check whether you're hitting those record ends with this. But as I say, we haven't covered unformatted output because really hope that you would never ever want to touch that. But it's maybe worth being aware that you can use IOStat if you hit errors while doing that to work out what's been going wrong. Well, I did actually mention stop earlier. So if you do just hit error after error and you just want to have your program quit early, if you just want to print an error message and quit, you can just do this stop and then give the message in a string. So that's your fallback if everything is broken, nothing is working, and there's no nice way to carry on with the code. Really, though, you should try to recover if you can. So this is considered the last resort. When you've got a file open, you can move between it, and I like the second one here. But firstly, backspace can be used to move back a record if you like. So you've got an open file, you can move backwards and you can move backwards in it after you've already read some way through it if you like. Also very useful, and we'll see this when we talk about namespaces tomorrow. Sorry, name lists tomorrow. Rewind. Does anyone have any idea why this is called rewind? I'd just like to ask that of people in the room. Why are we talking about using the word rewind to talk about going back to the back of the file? Data storage on tape, exactly. Yep, that's exactly it. Fortran still occasionally shows those really, really old signs of itself. And that's exactly what this is. This is saying if we've reached the end of the tape, we rewind it back to the start again. We're not really using tape much anymore. Of course, you can still use it for archival storage, but for most of us, day to day, we will not be writing or reading, writing to or reading from tape. But in the old days, it was used, so we've still kept the word rewind to talk about. We've got this open file. Let's go all the way back to the start again. So that's just a little bit of ancient style ancient style wording that's carried on to the modern day, which I actually quite like. I quite find the tapes and the punch cards and things a lot of fun, just because it's so weird compared to modern day computing. But that's possibly just me. I like it, but yeah, there we go. Okay, and at that we're right about at 4 o'clock. So there is an exercise here, and this is actually a really nice one to do. So, so what I'm going to say to people is, if you would like to have a go at this on your own just now or this evening, I would strongly recommend it. I think this is quite a nice little test of everything that we've covered up to this point. It's not too difficult, but what it does require you to do is to think about everything that we've done so far and to work out how to put it together into a working bit of code. It needs you to think about strings, it needs you to think about arrays, it needs you to think about converting between types to a degree, and it needs you to think about file output. What you'll be doing is just using the code to start from scratch. You're given a template program here. You then write a module that takes an array, which I think is defined in there for you. Yep, so this array is defined for you and it's called map. And what you do is you write it to file, and you write it to file in a format called PBM. And you can read about PBM if you click on the Wikipedia link here. And there's actually quite a lot of helpful information. And you'll see that it's actually a image format. It's a very primitive image format. The type of image we'll be writing is like this. A PBM is essentially black and white only. It doesn't do any shades of grey, no colors. And it's essentially, you can see here, it's essentially writing a 2D grid of zeros and ones. Where it's 0, the image is either black or white, and where it's 1, it's the opposite color. So that's what we have here. You can see how this draws these ones down here to form the letter J that we see in the image on the right. There's a little bit of a header. P1 should be the first thing written to file. P1 means that it's a 1-bit image, if you like, 0 or 1, black or white only. And then it tells you the dimensions of the image, 610. Because you could have it all in a single line. You can also write it like this. This is the same image, but because we've put 610, it knows that there are 10 rows and 6 columns. Something to be aware of here as well. Rows and columns are perhaps not the way around that you might expect. This is where you have to go between thinking about arrays as matrices and thinking about arrays as images instead. It needs you to be able to sort of flip the image in your head a bit. Yeah, if you want to come back here and use this as a reference, this is very good. But what you should be able to do is to take this and then write a module for it, and that module can take that array map and then write it out to file in a file called test49.pbm. And what it can do is it can hopefully then you will hopefully then be able to view that image. I'll just quickly show you what it looks like. So there is a solution that comes later on, but if you do this correctly, you should be able to get an image that looks like this. Black lines along the top and the bottom and diagonally down there. So this is a very nice thing to do. I would recommend having a go on it if you can tonight. That would be really, really great. If you don't have time, or if you just don't want to, don't worry, we'll come back and we'll talk a little bit about it at least tomorrow at some point. And we should definitely have an hour or two tomorrow afternoon just to work on code, to work on these exercises. And this, if you haven't done it at that point, is one that I really would recommend having a go at, because I think this is an excellent little test. Okay, so it's 4 o'clock, and we'll finish there. I hope that hasn't been too much. We have gone a little bit faster this afternoon to get through all this IO type stuff. I don't think it's been too difficult. It's just stuff to sort of power through. What was trickier, I think, was the material on arrays and functions and subroutines. Hopefully that's not been too much. If you do have any questions overnight that's come to you, if you're lying there panicking about modules or whatever at 3 in the morning, please don't worry. Just send me a email if you like, or just send a message tomorrow first thing, and we'll talk about it then. But otherwise, I hope that's been okay. Hope you all have a good evening, a good afternoon, end of the afternoon before then. I hope the weather's nice for you while it's nice here for me. And I will see you tomorrow morning. So yeah, have a good evening, and I'll talk to you again then. Okay, thanks. Bye, 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 everyone.